chemistry, which is acids and bases, or maybe the one that we hear the most about. So looking here just at properties of acids and bases, well, first question is, what is an acid and base? And actually, we have to define that scientifically here in another unit. But let's just look at some things that we know are bases and acids, and we'll look at what properties they have. So here's some bases in this image, and we can even make it bigger so everybody at home can see. If you put this on the TV, you can see it really nice and big. So some things that we consider bases. Notice lye, if you ever use lye, cleaning product. Baking soda, sodium bicarbonate, aluminum hydroxide. This would be like an antacid tablets, ammonia. All of these things would be considered bases. Some things that are considered acids, fruit. Here we have soda pop, some juice. Just very common things that are considered acids. Now, most of these are pretty weak acids, but we'll get to some that are a little bit stronger here in a moment. Here's a nice generic listing of things across our pH range. So our pH range, these would be our pHs, are what we use to describe the strength of our acids or base, their acid or base strength. And we'll get into the pH scale and how it's calculated in a moment. One thing I want to have you know, and again, we'll cover it in more depth as we go on, but each step, the pH scale, is a logarithmic scale, which means each step in the scale is a power of 10. So if we look at, say, lemons, and you see lemons, this is what always confuses people. You see lemons have a pH of 2, and you're like, wow, that's pretty strong. And then stomach acid is a 1. Well, really, it's only one step stronger. Well, not really, because this is a logarithmic scale. That's a power of 10 stronger. So if we look at the difference between grapes and lemons, that's, again, from 3 to 2 is a power of 10. So that means if we go from grapes to lemons to stomach, it's 100 times stronger of an acid. So a couple other things on our list. Notice it is based upon pure water. That's a pH of 7. Things that have higher pHs we think of as bases: eggs, baking soda, soap, up to things that are very strong like bleach and oven cleaner. So let's get on to what these properties are. So straight from your book here on acids, these are things we absolutely want to know. Aqueous solutions of acids have a sour taste. Tells us we shouldn't taste them, but they are sour. That's how they were first identified, is by their taste. And when I was in high school chemistry, we tasted them. We were encouraged to. I don't know why we don't do that anymore. The other thing, acids change the color of acid-base indicators. Very, very generic. Let's look a little bit more specifically at that number 2. So here we have the 3 main types of indicators that we use. First one, and one you probably use in 9th grade, is litmus paper. Litmus paper, if we have blue litmus paper, it changes red in an acid. So red in an acid. Red litmus paper changes blue with a base. So the way I remember it with litmus paper is blue. If it changes blue, it is a base. If it changes red, it's an acid. So litmus paper is a classic one. And again, we just use it to test whether it's an acid or a base. One thing we also have to be careful with litmus paper is whether, especially if we're testing it for a color blue, whether or not it's just wet or it is actually blue. Blue is blue. So don't confuse wet litmus paper with blue litmus paper. Another big one we use is called phenolphthalein. So phenolphthalein, I did have to pause the podcast to write it because and I think that's spelled right. Don't check my spelling, please. So phenolphthalein is a liquid. We put a couple drops of it into a solution to see whether a solution is acidic or basic. We use it very, very often when we're doing titrations, when we're trying to neutralize an acid or a base. A clear solution would be acidic. This would be an acid solution. A pink solution would be a basic solution. So the pink solution is basic. The clear is acidic. Now, thanks to Ben Susevich, I have to explain why one is a different color. And like I try to tell him, it's because the compound, the formula actually changes based upon the acidity of the solution that it's in. So here's the structure of phenolphthalein. Now, a lot of things that have colors, the reason they have colors is because they have a lot of double bonds, one away from each other. So with these alternating double bonds, this is what we'd call a conjugated system in chemistry. Well, here it is an acidic solution. Notice it has a couple alcohol groups. Well, if it's in a basic solution, it's going to rip those hydrogen ions away. And notice it also breaks this bond. And so we've actually dramatically altered the structure of the compound. And now we have, again, all these conjugated double bonds that can absorb and reflect light, giving it a color. That is a great explanation, but at least it gives us a start towards it. So a lot of times when we have alternating double bonds like that, it is a structure that can be colored. In addition, again, to our transition metals that we spoke of before. Last one is here. So we have litmus paper, that's an important one, again, to remember the colors of. You will have to remember the colors that acids and bases make with litmus paper. It's just something that chemists know. Same thing with phenolphthalein, because it is so common, it's just something we know. You don't have to memorize the colors. This is called universal indicator, or UI or UVI sometimes. This universal indicator, notice it has a color wheel that normally comes with the paper, and you match the color up to get a better predictor of the pH. Now this is when we want to know the actual pH and not just whether it's an acid or base. There's a use for both things. This one, I'm not going to expect that you memorize all the colors of universal indicator. Just know that it's there. It's one of the things that we use. Again, primarily we're going to use phenolphthalein. We're going to go to use litmus paper, and we need to know the colors of those indicators. Okay, so we talked about indicators. We talked about tasting acids. And you do taste acids, actually. Whenever you taste things that are lemons or fruit that are really strong, you can taste their sourness. Okay, number 3. Some acids react with active metals to release hydrogen gas. So we've seen these reactions before. Notice, here's an example, barium with sulfuric acid, making barium sulfate, which is a salt, and hydrogen bubbles. So we did this a lot with magnesium. We had magnesium with, say, hydrochloric acid. We've done this multiple times for multiple different experiments, making magnesium chloride as our salt and hydrogen gas. So acids like hydrochloric acid, sulfuric acid, react with many metals to form hydrogen gas. Now, which ones do they react with? Well, all we have to do is look at a reactivity series. So hydrogen is included on a metal reactivity series for this reason very often. Notice all the things above hydrogen it will react with, and it will replace. Notice hydrogen doesn't react with all metals. It doesn't react with what we think of as precious metals, our gold, our platinum, our silver, or copper. So those are less reactive than the hydrogen. They will not react with it. But any of these, zinc, aluminum, magnesium, some of our favorites are on here. Even iron will react with acid, tin, lead. All of those things will react, produce hydrogen gas. Now, the level of reactivity depends upon, again, the difference, the further it away is from the hydrogen. So lithium would be the most reactive with hydrogen. Lead would be the least, active reaction. So we know acids react with metals. They form hydrogen gas. We can look at that. One other acid-base reaction, well, we'll get to that here in a moment. Here's the big one that we're going to look at actually here is acids and bases react to produce salt and water. So the main reactions that we look at are acid-base reactions. So we could have sodium hydroxide plus hydrochloric acid, and they react to form, it's really a double placement reaction, but it's a type of double placement reaction we call an acid-base reaction. So we form salt and water. This is going to be our most common type of acid-base reaction that we'll look at. Now we'll have different acids and bases thrown in, but anytime we have an acid, we have a base, we're going to form a salt and water. And that's going to be neutralized. So the acid can neutralize the base, and we can form salt and water. When we look at different examples, what the difference is going to be is just what the salt is. So, like in that example, if we have sulfuric acid, which is another strong acid, that's reacting with sodium hydroxide, our base. Well, we'll still form water. We'll take out the hydroxide. The hydrogen ions will form water. And then our base this time is the sodium with the sulfate, Na, in this case 2SO4. So we could throw any acid and base together and do a similar thing. We know it's water, and whatever the other ions are going to make up our salt if we have a strong acid-base reaction. Let's try just one more, maybe barium hydroxide. Now, our reactions like this, maybe something like acetic acid, HC2, H3, O2. These also will react. Again, our hydrogen with our hydroxide makes our water, and the ions that are left will make our salt, barium, and in this case, acetate. So it's going to take some practice to make sure we know our ions, our polyatomic ions. We can take them apart and rearrange them as the reaction needs. Okay, so now we looked at some acid-base reactions that produce salt and water, producing a neutralized reaction. The other thing I want to look at that it doesn't include here is carbonate reactions. Carbonate reactions are very common, and ones you have experience with, because carbonates are basically antacid tablets. So people take antacid tablets to neutralize acids that are in their stomach. So this classic reaction is, again, notice hydrochloric acid and sodium carbonate, in this case, make a salt and water, just like an acid-base reaction. But because we have a carbonate, we have one additional piece to it. We have carbon dioxide bubbles that are coming off. So the carbonate produces carbon dioxide. Actually, anytime we see a carbonate, a lot of times when the carbonates react, whether it's with an acid or whether it's through decomposition, CO2 is often a product of a carbonate reacting with something. So here we have sulfuric acid, and we have just a different carbonate, ammonium hydrogen carbonate. So don't get confused that it's something different on it. If it's a carbonate, water, whatever the salt is, and carbon dioxide. And here's a little picture for you. Last thing that's on this list is it says some acids conduct electric current. Well, that's very helpful. Well, here's the difference. A lot of our strong acids will conduct electric current because they're fully dissociated. Some of our weak acids will not so much. So it's kind of something where we have to figure out what's strong and weak, and we don't really know that yet, but we will soon. Okay, let's name some of these acids. So here's our naming system that we didn't touch on before, but now we absolutely need to know. If we have a single element ion, I mean like fluorine, chlorine, bromine, anything that's straight from the periodic table. Let me pick something else. If we have oxygen, and oxygen's directly attached to only hydrogen, like this, well, then its name, it becomes a hydroic acid. We put hydro on the beginning, its name, ic, and acid at the end. So notice fluorine connected to hydrogen is hydrofluoric acid. Chlorine attached to just hydrogen is hydrochloric acid. Hydrogen on a bromine, hydrobromic acid. If we looked at water and we named it by our acid naming rules, which we could, it'd be hydroxic for the oxygen acid. So anytime we have a single element ion with only hydrogens attached, we can name it by our acid naming rules. We're going to have a hydro beginning, ic ending, and acid. And whatever the element in question or the ion in question is, goes in that spot. Now, we don't only have single element ion acids. Unfortunately, we have a lot of different ones. What's nice about it, though, is the naming system is built off of all of our polyatomic ions. So if you did a really good job on learning your polyatomic ions, acid naming is going to be really easy. Obviously, if you didn't, this is going to be a bit more difficult for you. Okay, so if we have something simple like carbonate, and it has, let me zoom it in on just this carbonate so we don't have to be confused by everything else. So I have my carbonate. Carbonate with an ATE ending is CO3-2. If it's connected to only hydrogens, we're going to change its ending. Notice no hydro beginning. That would be something different. It only has an ic and an acid ending. So ates become ic acids. Ates become ic acids. So that's true for any polyatomic ion that ends in ATE. Notice another big one that's very important is nitrate. Nitrate, ATE, NO3-1. Add only a hydrogen, and we get nitric acid. Phosphate, ATE, add only hydrogen, this times 3. So it doesn't matter the number of hydrogen, it just matters the ending on the polyatomic ion becomes an ic acid. You'll notice there's other things besides ic acids on this list, and those are OUS acids. Where those come from is if we have ITE endings. So let's look at some that are a bit more common. So notice we had nitrite, and we've talked about how we have nitrate, and we've talked about how nitrite just has one less oxygen. Well, its acid name is different as well. If we just have hydrogen attached to it, ITE polyatomic ions become OUS acids. So nitrite is nitrous acid. Chlorite is chlorous acid. And so that's where our naming system comes from. Phosphite is phosphorus acid. Okay, so obviously we can run into some confusion. For example, let's look at some. So H2SO4, this is our sulfate ion. Sulfate bonded to only that hydrogens, we could name this sulfuric acid. And you're like, yeah, I know what sulfuric acid is. That's fine. That's not difficult. However, say we have the sulfite ion. Sulfite is SO3. Also has a -2 charge, so it's H2SO3. This, because it's an ite, becomes sulfurous acid with an OUS ending. Sulfurous acid. Now, here's where it gets even more fun. If we just have sulfur by itself, sulfur tends to have -2 charge. If it only is bonded to hydrogens, this is hydro, again a hydro beginning, sulfuric acid. So notice the difference in all of our endings. We can have an ic acid ending, we can have an OUS acid ending, or we can have a hydroic acid. And it all depends again on what our either anion is or a polyatomic ion is. Well, let's finish by looking at some base properties and wrap this up. So we do have to know our acid names. We do have to know properties of acids. We do have to know their general reactions with metals, with acids, with carbonates, the colors they might turn, indicators. And we also need to know their names, obviously. We also need to know some stuff about bases. Bases tend to taste bitter. Bases also change the color of acid-base indicators that we already looked at. Again, we need to know the things they do with from our base standpoint as well. So again, in phenolphthalein, they tend to be pink. They turn litmus paper blue, and obviously we can use the universal indicator, and then we pick off the color that way. Again, bases tend to be our darker colors. Our acids tend to be our lighter colors on universal indicators. And I just hear someone asking a question, well, what's a universal indicator? A universal indicator is actually a mixture of multiple indicators, so you get a different color range. It's kind of an ingenious solution to get multiple pHs. Anyway, here we go. What else do we know about bases? Bases tend to feel slippery. They're in soap, so they have a slippery feel. They react with acids to produce salts and water, exactly the same thing we said. And here they conduct electric current. So most, especially strong bases, are also ionic compounds, and so they completely dissociate and they will conduct electric current. So I said we'd talk a little bit about the strength of our acids and bases. Okay, what a strong acid is a strong acid is something that fully dissociates. So these are things that fully dissociate. What do I mean by that? I mean, when we put the sulfuric acid in the water, we get the sulfuric acid loses its hydrogen ion, actually loses it to water. It ionizes the water to form something that's called hydronium, which is very important. So our hydrogen ions, even though we talk about producing hydrogen ions, the hydrogen ions don't really exist. The hydrogen ions right away attack the water and we get hydronium ions. So strong acids fully dissociate. So if you had 1 molar sulfuric acid and you put it in water, that means you actually have 1 molar hydronium ions. You don't really have the 1 molar sulfuric acid anymore. You have 1 molar hydronium ions. Weak acids, on the other hand, partially dissociate. So they partially kind of come apart to make hydronium. So notice that's why we have this equilibrium symbol, because they don't go to completion in one direction. So anytime you see an arrow like this, it means the reaction goes only in one direction and it goes to completion. Now that we put it in an equilibrium, that means the reaction can go either way. So notice, sorry I was interrupted. I don't even know what I was talking about. Partial dissociation of acids. Notice, again, sulfuric acid, and this is something we have to talk about, a lot of things we have to talk about with acids, has 2 hydrogen ions. Because it has 2 hydrogen ions, it can actually act as an acid twice. It can give up 1 hydrogen ion to water, make hydronium. And notice over here, it can give up another hydrogen ion to water and make more hydronium. However, this second version of it, hydrogen sulfate, as I might call it, it is not a strong acid. In this case, it's a weak acid. And it partially dissociates. Notice some other things that are weak acids. Notice phosphoric acid, H3PO4, is a weak acid. Notice that gives up 1 hydrogen ion, and we have H2PO4, which also, I'm going to tell you a secret, can act as an acid again. So this is something, by the way, I'm going to throw some words at you. It's something we'd call triprotic. So it has 3 hydrogen ions. So it can act as an acid 3 times. Isn't that fun? Not everybody can do that. Phosphoric acid can. But it doesn't mean it's stronger. It just means that it can do it. Now let's look at some strong and weak bases. Our strong bases are almost exclusively things that have hydroxide ions. At least at this point, based on our current definitions of acids and bases. So if they have hydroxide, they completely dissociate in water. They produce hydroxide ions. Again, notice the arrow going only one way in completion. Weak bases do produce hydroxide ions, often in solution, but again, not as much. They don't completely produce hydroxide. They don't completely dissociate. In this case, this is a base because it can take a hydrogen away from water and that way produce hydroxide, but it can't do that fully into completion or a full dissociation as we see with our hydroxides. So that is properties of acids and bases. Next time we're going to get into acid-base theories. We'll compare Arrhenius and Lewis acid and base theories.